All right, hi everyone. Today we are starting chapter 8, and this chapter is all about similar figures. So it's about shapes that look similar in shape, but they are going to be different sizes. Think back to when we learned about a dilation, right? So if you have a triangle like this, let's say we dilate that triangle so that it gets bigger. These are called similar figures because they look similar, but they're not the same size, right? So it's different than congruent. We learned about congruence. We've been talking about congruent shapes for a long time. And this whole chapter is going to be about similar. The symbol for similar, by the way, it's basically a congruent sign, except it doesn't have the equal sign. It's just this little squiggly thing. So if you ever just see this little squiggle here, that is the symbol for the word similar, okay? It just basically means a dilation has happened. So it's like a shape that is either a bigger or smaller version of the other shape. So a lot of this is going to be review, but we're just kind of setting up this chapter and talking about some properties about similar polygons. So what are similar figures? So they're going to have the same shape. So they're going to look the same, but they're not going to be the same size. So not the same size. And as I just mentioned, they are created by dilations. That's something we learned about a long time ago. So they're going to be either enlarged or reduced by a scale factor. And if you remember from when we learned about scale factors, we use the letter K when we're talking about scale factors. So similar figures, they're going to have the same angle measures. And again, that's something we already know because they're dilations. So if something has been dilated, they have the same angle measures. They obviously won't have the same side lengths, but they're going to have the same angle measures. Now, something that will be true about their sides, the sides that correspond will be proportional. And I'll talk more about what that means in a second, but these are going to be proportional. It just basically means that their scale factors are going to be the same. So if you take any two sides and you compare them to the corresponding sides of the other shape, they should be the same scale factors. They should be proportional. And as I said, the symbol for similar is this. It's kind of like the congruent sign, but no equal sign under it. Okay, so for right now, we're just going to practice the basics. In this picture here, we have these two triangles, and they tell you right here in the directions that they are similar to each other because they have that similar symbol, right? So that means that this was a dilation, right? They're similar figures. It says find the scale factor from RST to XYZ. So that means we're starting from this shape, right? We start from this shape, and then we go to that shape. As you can tell, the shape got smaller, right? So it started, this size, and then it got smaller. So we would expect our scale factor to be something small, something that's less than 1. So here's how you do scale factor if you forgot. You always do the new divided by the old. So we're going to take the new shape, which is the smaller shape, and we're going to divide that by the first shape. And you can pick any sides, they just have to go with each other. So for example, the 20 over here, that corresponds with the 12. The 25 corresponds with the 15. And the 30 corresponds with the 18. Most of the time you're going to be able to tell by looking at the shape, but you can also tell by looking at this statement here. And we've done this before, right? The first two letters are RS. That means that side has to correspond with XY because those are the first two letters in that one. And if you look at the picture, that makes sense, right? RS corresponds with XY. Okay, so anyway, scale factor would be new divided by old. So just pick any two sides that go together here. 12 divided by 20, and you're just going to write that down. So 12 divided by 20. You can divide it out and make it a decimal if you'd like, or you can just reduce the fraction. I prefer to just reduce the fraction. So this is 3/5. Now, if you check all the other sides, it should also equal 3/5. So for example, 15 over 25, that also equals 3/5. And you can check the third one as well, 18 over 30. If you reduce that, that also reduces to 3/5. So as you can see, they all have the same scale factor. So our scale factor here is just 3/5. Okay, it says list all pairs of congruent angles. All the angles are going to be congruent, so just list the ones that correspond with each other. So angle R goes with angle X. You can tell by looking at the picture. You can also tell by looking at the statement here. R goes with X because they're the first letters. So angle R is congruent to angle X. And then we're just going to list the other ones. Angle S is congruent to angle Y. And then angle T is congruent to angle Z. And then finally it says write the ratios of the corresponding side lengths in a statement of proportionality. So here's what a statement of proportionality is. It's basically when you list the scale factors and you just say that they're all equal to each other. But we're going to use the letters of the sides instead of the actual numbers. So for example, let's take side XZ. Okay, I'm going to start with XZ. If I look at where XZ is over here, that's the one that has the 15 on it. That side corresponds to the one over here, the 25, right? That corresponds to RT. So I'm going to say XZ over RT. That has to be equal to all the ratios of the other sides. So I'm just going to pick another set of sides. So I went from XZ to RT. We're going to do another side here. Let's do XY to RS. Those go together, right? So that would equal XY over RS. And then that would also equal the third side, which would be ZY over TS. So if you're ever asked to do a statement of proportionality, that's what this would look like. You're just making three ratios and you're saying that they're all equal to each other. Okay, let's take a look at the next page. So we're going to practice finding corresponding lengths now. There's a couple different ways you could do this. You could just use scale factors, and if that makes more sense to you, you can go ahead and do that. But I'm going to show this using a proportion, just because this is the easiest one to not mess up. So let's take a look at this first example. They want you to find the letter X. Now, again, one thing you could do is just figure out that scale factor and then use the scale factor to figure out what X would have to be. But I'm going to set up a proportion to solve this. So you just take the side you're trying to find, which is X, and you identify the side that corresponds to. It corresponds to the 30 over here. So I'm going to say X over 30. Now the order doesn't really matter. You could also say 30 over X. Doesn't matter. What matters is that you set the second one up the same way that you set the first one up. So for my second ratio, I'm just going to pick another set of sides that correspond. So maybe the 15 and the 18 here, okay? So if X over 30, that's a ratio, that's going to equal 15 over 18. Those ratios are supposed to be equal to each other, right? Because that's how scale factors work. This divided by this should be the same thing as this divided by this. And now that we have this set up, this is called a proportion. So whenever you have two ratios that are equal to each other, it's called a proportion. And a quick way to solve these is just cross multiplying. This is something that you probably learned a long time ago. So I'm going to cross multiply here. 18 times X is 18X. And then 30 times 15, that is 450. And then to solve for X, you could just divide both sides by 18 here. So X would equal 25. There we go. That's the missing side. So that's one way you could find missing side lengths, is just setting up proportions like this and then just cross multiplying. Okay, again, you can use scale factors too. I'll show you that maybe tomorrow. But for the rest of this notes, I'm just going to do the proportion method. So in our next example, they tell us that the triangles are similar, and it says find the length of the altitude PS. The word altitude just means height. So they're looking for this piece right here, the length of that. So let's just call that, we'll just call that X for now, okay? I'm going to set this up the same way. So now I know that this is not technically a side length. It's it's an altitude, but it's still going to be proportional with the other shape. So we could say X over 20 equals, and then just take, any two other sides that go together and set those equal to each other. So you could use the whole side if you want to. 6 plus 6 is 12, and then 8 plus 8 is 16. So you could set it equal to 12 over 16, or you could just use the little half pieces, right? 6 over 8, that would work. So here we go. X over 20 equals 6 over 8. Now notice I didn't put 8 over 6. The order does kind of matter here, right? Like if I started with X, then I have to start with 6 because I went from the small shape to the big shape. So you have to do that the same way both times. Small to big, small to big. Now let's go ahead and cross multiply here. 8 times X is 8X. 6 times 20, that is 120. And then you can just divide both sides by 8. So x is 15. So that's our altitude. That means our altitude is equal to 15. Okay, so there's a couple more problems that you can try here. I think for the sake of time, to make this video not be so long, I'm actually going to skip over these. If you want to try them on your own, I will tell you what the answers should be. You can go ahead and write these down if you want, maybe try them on your own time. This one should be 8. And then this one over here, you should be getting km should be 42. So if you want to, if you're watching this from home, go ahead and pause the video, maybe try these problems until you can get these answers. But just for the sake of time, we're just going to move on here. Okay, let's go ahead and go to the next page. We're going to look at some examples that have a little bit of algebra in them. Now you can still do these with proportions. So that's how I'm going to be setting these up. So here we have two triangles that are similar. They tell you that they're similar right here in this statement. This is a good example of where you might actually want to use the statement to match up the sides, because it's kind of hard to tell by looking at these triangles which sides should go together. So I'm going to go ahead and color code the sides right now. So let's look at AG. So AG is the first two letters. That's supposed to go with KX. So this 32 right here, that's going to correspond with this side over here. So I'm going to just color code all these real quick. And then let's see, GM, the last two letters, that's going to be with XD. So GM goes with XD. And then that means those third sides correspond. It is very helpful to know which sides correspond with each other. It's going to help you set up your proportion. So it says find the value of X. All right, let's just try to set something up here. So if I take this pink side, that pink side corresponds with this side over here. So I'm going to write that as a ratio, x plus 6 over 36. And then we're going to set that equal to another ratio. So if I look at this one, x plus 3, that corresponds with the 32 over here. So I'm going to set it up the same way, x plus 3 over 32. And then from here, you can cross multiply. You're just going to go like this and this. Now this is going to involve a little bit more algebra, right? Think of this as 32 times x plus 6. You're multiplying it by both of those. So it would look kind of like this, 32 parentheses x plus 6. That's going to equal the other side. So 36 times x plus 3. And then from here, you can just go ahead and solve this out. So you can distribute that 32, distribute that 36. This would give us 32x plus 192 equals 36x plus 108. And then if I move this 32x to the other side here, we would have 192 equals 4x plus 108. And then you could subtract that 108. That's going to leave you with 84 equals 4x. And then finally, you could just divide. So x is 21. So that's how it works with the little algebra. You can still set up your proportions. It's just going to be a little bit longer to solve for x. And then over here, we have two similar triangles, but they're kind of overlapping each other. So this can be confusing to look at. It might be helpful to redraw these as separate triangles. So let's look at the picture here and start labeling what they give us. They tell us that BR is 4x plus 7. That's this whole length right here from B to R. And then they also say that BG is 18. So that's from here to here. That's 18. Okay, so again, it might be helpful to think of this as two separate triangles. So if you are looking at BNV, for example, BNV is this smaller triangle. I'm going to bring that out here and relabel it. So it's 8, 10, 12, right? That's B and V. And then the bigger triangle, BRG, that's this outer triangle here. I'm going to label that also on the outside. And the bottom side is 18. This side over here, we don't know what this is, but we do know that this side is 4x plus 7. There we go. So this is BRG. Okay, and again, it might be helpful to just kind of look at this picture instead, because you can see that they're two separate triangles. If you don't need to do that, that's fine. You can just leave the picture like this, but it might help us set up our proportion here. So let's go ahead and set up our proportion. We've got 4x plus 7. That's going to go with 12. 4x plus 7 over 12, and that's going to equal the 18 over the 8. Now again, you can also, you can do both of these the other way around if you want to. And then from here, you're just going to go ahead and cross multiply. I think for the sake of time, I'm going to skip this step. It's kind of similar to the other one that we did. You would cross multiply, and then you're just going to solve for x. So if you do this correctly, you should be getting 5 for x. So if you'd like to try to solve that out on your own, you can. Okay, the last thing we have to talk about is how scale factor works with perimeter, area, and volume. So let's start with perimeter. So with perimeter, it's the same as all of the other problems that we were doing. So the perimeter of the sides are also going to be proportional using that same scale factor. So as long as the polygons are similar, then their perimeters will also be proportional. So it's kind of the same thing that we were doing before. So let's just look at this first example here. It says a town plans to build a new swimming pool. An Olympic pool is rectangular with a length of 50 meters and a width of 25 meters. I'm just going to draw that real quick. So this is our Olympic pool, and they give us the length and the width. So we'll call this one 50 meters, and then this is 25 meters. Okay, the new pool is going to be similar in shape, but it's going to have a length of 40 meters. So it's going to be, looks like a little bit smaller, right? So the new pool is going to have a shorter length here, so it's 40 instead of 50. It says find the perimeters of an Olympic pool and the new pool. Well, we can get the Olympic pool pretty fast, right? So we know that this is shaped like a rectangle. So the perimeter of the Olympic pool is just all of this added together. So that would be 50 plus 50 plus 25 plus 25. That is going to be 150. So the perimeter of the Olympic one is 150 meters. Let's find the perimeter of the new pool. So there's a couple different ways you could do this. You could find this side length if you want to, but you don't actually have to, because we have one side and that's enough to make a proportion here. So remember, the side lengths are going to be proportional, but so are the perimeters. So what we could do is we could say the perimeter of this one, let's just call it x for now. We don't know what it is, so we'll just call it x. And then we're just going to make a proportion. So x over 150, x over 150 equals 40 over 50. So I just took the ratio of the perimeters and I set it equal to the ratio of the side lengths, because they should be proportional. And then again, you can just cross multiply here, solve for x. That would be 50x equals 6,000, and then you could just divide both sides by 50. So x is 120. So that would be the perimeter of the new pool. Okay, let's talk about area and volume now. So with area and volume, it is a little bit different. Oh, we have another example with perimeter. So we can do that one first if you'd like. So it's kind of like the other one. It says find the perimeter of gazebo A. So the perimeter of this one, we have no idea. Let's just call it X. We also have no way to find it at the moment, right? Because we don't have any of these sides. The only thing we know is that this is 10. But we do know the perimeter of this one. If you just add up all of those sides there, you'll have the perimeter of that one. And I believe it is 69. If you just add up all of these, it should be 69. So we can set this one up kind of the same. We can say x over 69 equals, and then now you're going to set two sides as a ratio. Now we kind of are limited here. We have this side of 10, so we have to use that. So 10 over that one corresponds with 15. And then from here, you could just cross multiply. I'm going to skip that step for now, but you should be getting 46 for x. Okay, with area is a little different. So if two polygons are similar, then the ratio of their areas is equal to the square of the ratios of the side lengths. And the reason why this is happening, it's because area is a measure of square units. So remember when we did area before in some other examples in the past, and it involves square units because you're taking a length and you're multiplying it by another dimension. So it's like two-dimensional. So here's how you're going to use proportions with area. So in this diagram, they tell you that the triangles are similar. Okay, it says find the area of DEF. Now we have the area of ABC, so we need the area of DEF. So the area of this one, we don't know, let's just call it X. Now I do have a scale factor, right? It went from 5 to 10, so this shape is 2 times bigger than this shape. So you might be thinking, oh, well then the area is just going to be half as much as this. But that's not how scale factors work with area. So instead, you take the side lengths that go together, so these two correspond with each other, and we're going to square those. So we'll say that the ratio of this area to this area, so x over 36, it's going to equal the ratio of the sides squared, because it's area. So you just take the ratio of the sides and you square those. You're just going to literally square both of these numbers. So that would turn into, let's see, 5 squared is 25, and then 10 squared is 100. So here's our proportion now, and now you could just cross multiply like we've been doing, and then you could solve for x. So that would give us 100x equals 900, and then you could just divide, so x is 9. So that means the area of that smaller one is 9 centimeters squared, and as you can see, it's not half, right? Because that's not how it works. So it is 36 compared to 9. That's actually 4 times smaller, and that makes sense because the scale factor here was 2, and 2 squared is 4. So that means the area is going to be 4 times smaller instead of 2 times smaller. So again, you just take the scale factor of the sides and you just square it, and you can set that equal to the areas. So let's look at the next one over here. Same thing. We want the area of this bigger rectangle. I'm going to call that one x. So if we say x over 84, and then we make a ratio of the side lengths here, 21 over 7, that's going to equal 21 over 7, except we have to square that, okay? Now, if you want, instead of squaring both of these numbers, you could just divide these numbers first. That might make it easier to work with. Like 21 divided by 7, that's just 3, and 3 squared is just 9, right? So this would be x over 84 equals 9 over 1. Or you could square both of these numbers and end up with big numbers here. That's okay too. It would work the same way. And then we can just cross multiply here. So that would be x equals 9 times 84, which is 756. So that would be the area of that one. Again, if you squared the 21 and the 7, it would work that way as well. You'd have x over 84 equals 441 over 49. And if you cross multiply these, you would still get this as your final answer in the end. Okay, and then finally with volume, volume is almost the same, except volume is a cubed dimension instead of a squared dimension. So instead of squaring the scale factor, we're going to cube it. So let's look at that last page here. So if two volumes are similar, then the ratio of their volumes is equal to the cube of the ratios of the corresponding side lengths. So this one's going to be very, very similar. So if we're finding the volume of this missing figure here, so they tell us that these figures are similar, what's the volume of figure B? So volume equals, let's just call it x. So we can say x over 38 equals, and then now we're going to take the ratio of the sides. So this one's 9, this one's 2. So it's going to equal 9 over 2, except we have to cube that because this is volume. So the ratio of the volumes is always the cube of the ratio of the sides. So let's do that. We can do 9 cubed and 2 cubed. If you just type those in your calculator if you need to, that's going to turn it into 729 over 8. And then I'm just going to copy down this other ratio. And then now we can just cross multiply here. So we would have 8x equals 27702, and then just divide by 8. So then that new volume should be about this much, 3462.75 cubic centimeters. So that is the volume of figure B. Okay, this last example is very similar. It's about the Olympic pool again, except this time it's a volume problem. So an Olympic pool has a volume of 2,500 meters cubed. So just imagine like a pool. I'm going to try to draw a 3D like rectangle here. So if we have this Olympic pool, the volume of this is 2,500 meters cubed. And the pool has a length of 50 meters and a width of 25. So just imagine, this is 50 meters, and then that width is 25. Okay, so they're building a new pool that's similar to the Olympic one, and the new pool is 40 meters long. So this is very similar to that Olympic pool problem from before. So we have 40 meters here, and then we don't have any other measurements about this new pool, right? So this one's the Olympic one. This one's the new one. It says, what is the volume of the new pool? So I'm just going to put volume here. We'll call it X. And then we can just make a ratio for this. So we have X over 2,500 equals, and then I'm going to take the ratio of the sides, 40 over 50. And because this is volume, we're going to cube that ratio. Now, before you cube these numbers, you can reduce the fraction first to make this easier to work with. Like 40 over 50, if I drop those zeros, it's the same thing as just 4 over 5. So I'm just going to get rid of those zeros. And then we're going to do 4 to the third, 5 to the third. So we would have X over 2,500 equals 64 over 125. And then from here, you could just cross multiply and solve for X. So we would have 125X equals 160,000. And then we could just divide by 125. So X should equal 1280 cubic meters. Okay, that is it for the notes. So now you can go ahead and start your homework.